to say that we proposed this workshop like 2 years back to the ICTP. So the original idea was to have a real workshop in the sense of having a couple of talks, like 2 or 3 per day, and a lot of time for discussion in the whole week, right? But COVID changed everything, and now, well, we hesitate a lot, but finally we decide to keep going with the workshop, but with a kind of different format. So now we have like just like 3 days, 3 half days actually. And yeah, the idea is to have like a long discussion at the end of the session of each day. So, and the other thing is that it was kind of complicated to find uh, the schedule because, for instance, for Stefan, it's super early. It's like 5 a.m. now. He's at Santa Cruz. And for Hyun Min, it's super late at Seoul, like 10 p.m. So we'll finish like at 2 a.m. So sorry for that. The other thing is that this workshop belongs to to a program, a 2-week program. So last week we had the third South American dark matter workshop. This week is the workshop on new trends, and next week we'll have the Latin American workshop on observational cosmology. So you guys are also super welcome to join. I don't know if I'm missing something. So of course we want to thank the ICTP for hosting us, even if it's just virtually, but maybe next time we'll be able to do it like a real in-person meeting. So I think that's on behalf of all the organizers, so Rogerio, Joseph, Farinaldo, and Stefano. So again, we welcome you, and I think we can get started. And so Farinaldo, you want to?
Yeah. All right. So thank you very much, everyone, for attending this workshop. Well, it's quite nice. We have so many speakers and interesting topics. So let's get started without further ado. Today we start with Hyun Lee. We will talk about exothermic self-interacting dark matter. So please share your screen, and you have about 25 plus 5 minutes, okay? As soon as you get close to the end of your talk, I will interrupt you. Just say, look, you have 5 minutes left.
Okay. Thank you. Thank you for your kind invitation. So today I'm going to talk about exothermic self-interacting dark matter. Maybe a little bit self-interacting, but mostly exothermic dark matter in this talk, in light of general one-ton excess recently reported. This is based on my own paper in last June, and another paper coming out probably tomorrow. So let me first give you introduction and also a little bit about kinematics on exothermic dark matter and models in a model independent way, and then I will going to discuss microscopic models and then conclude. So one word, just a few words on this self-interacting dark matter, just because of the conflict between observed the velocity curve in galaxies and as compared to what we see, what we predict from the embodied simulations without baryons. So this is called core cusp problem. So similar observed profile favors core dark matter profile, and then there are related problems at small scales, such as too big to fail and diversities for the same halo mass. And self-interacting dark matter has been around us for many years, and because it helps to solve the small scale problems by transport heat from outside to inside in the dark matter distribution, such that dark matter profile becomes more cold. The self-interaction cross-section required to solve the small-scale problems around this ballpark cross-section between 0.1 and 10 centimeters scale per gram. But the Billy cluster bounds constrain dark matter self-interaction to be less than 1 centimeter square per gram. So there might be some velocity dependence in the self-interaction. And on the other hand, we have been looking for dark matter for many years, in particular by direct detection experiment. In Xenon 120 in particular, has been looked for WIM dark matter with a recoil energy more or less smaller than 50K electron volt. And then event rate can be calculated depending on the dark matter density and the particle physics input for scattering cross-section between dark matter and nucleon. But the most normally self-emitting dark matter tends to be light, so it may produce too small recoil energy to be observed below threshold. But the on another end, and also dark matter, light dark matter could be very different as it comes to the dark matter direct detection. In the case of dark matter nucleon scattering, so in the case of dark matter nucleon scattering, the recoil energy is very small. So we need to have lower threshold energy by considering cryogenic semi-conductors. So in the case of dark matter electron scattering, we are in a better shape because of the light target materials, such as semiconductors or superconductors. So even though the threshold recoil energy is small, about up to 10 electron volt, we may be sensitive enough to probe dark matter interaction through dark matter electron scattering. So this has been discussed for a long time. But now, when we see the excess from Xenon 1-ton electron recoil energy, as you can see here, the event as a function of the recoil energy, there is the excess between recoil energy between 1 and 7 keV, and this excess is about 3.3 deviation from null signal. Most significant excess appears around recoil energy equal to 2 to 3 electron volt. Of course, there are background explanation for this excess, such as unknown tritium or argon-37. But in this talk, I will focus more on the dark matter interpretation. So already in the Xenon 1-ton paper, they come up with two explanations, standard explanations, the solar action or KV scale dark matter. So solar action is warm because the action is produced in sun, but the KV scale dark matter is cold, and just the mass scale is related to the recoil energy. But the on one hand, the solar action, in the case of solar action, it is possible to explain this bumpy feature in the recoil energy, but it is a strong conflict with a star cooling bound, such as red giant stars and white dwarfs, etc. But the cave scale dark matter, it is okay with a star cooling bound, but the feature is that it's a monochromatic recoil energy. So in this talk, I'm going to talk about inelastic dark matter case. In standard elastic scattering between light dark matter and electron, the recoil energy is bounded about electron volt or 10 electron volt if you take into account electron velocity. But so it is not possible to explain observed electron recoil energy in Xenon 1-ton. So we need to consider another mechanism to produce large recoil energy. So one possibility is to consider inelastic scattering between dark matter and electron. So already some of the similar work have been published, including Harigaya and Brahmanti and the SE, etc., around that time. So the basic idea is to consider two-component dark matter with a small mass splitting, and that mass splitting about 2.5 electron volt. So in that case, if dark matter downscattered from heavier state to the lighter state, it is possible to kick the electron with a sufficiently large kinetic energy because of the energy conservation. So even with the standard dark matter halo model, it is possible to explain the large recoil energy observed in general one-ton. This is called exothermic dark matter. So, but if you go to general atoms, electrons are not isolated; those are bound to general atoms. So it is very complicated. So first, we need to consider electron velocity. Second, electron is bound to a nuclears. We need to consider a nuclear recoil energy, and also electrons are bounded. So we need to we need to use ionization energy to ionize electrons in the first place. So then, so of course because of the energy conservation, the energy lost by dark matter and the nuclear recoil energy, is possible to infer what is the remaining energy delivered to electron in this form. So in the standard form for elastic scattering process, for the elastic scattering, we don't have the first term. But if there is a mass splitting between the two states, we need to include the first term. So mass difference is very important. And typically, nuclear recoil energy can be ignored. So for the later discussion, I'm going to ignore the nuclear recoil energy. But we can, in principle, keep the electron velocity because electrons are moving around inside general atoms. So we need to include, consider electron velocity and dark matter velocity at the same time. And just by using the energy conservation before and after scattering between electron and dark matter, it is possible to infer the electron recoil energy as well as momentum transfer exactly. So this is the exact expression as a function of input information, which is the dark matter kinetic energy and electron kinetic energy. But this full expression is a bit complicated. So let me make certain approximation by assuming that the dark matter momentum is larger than electron momentum, which is the case when dark matter mass is larger than 10 mega electron volt. Then in this case, when the mass splitting is smaller than the electron mass and then the dark matter is heavier than electron, we have you can define the expansion parameter kappa, which is the ratio of the mass difference divided by the relative kinetic energy. So in this case, recoil energy is approximated to this form, which depends strongly on the mass difference between the dark matter particles. And the momentum transfer is just to follow standard relation between energy with the energy. So just also a momentum transfer is determined dominantly by the mass splitting. So of course, in the other case, for the light dark matter, the electron momentum is more important. Then nonetheless, we can still define some expansion parameter kappa tilde. That is again mass difference divided by the relative kinetic energy. So then again, the recoil energy is a little sensitive to the velocity. Just mass difference determines both electron recoil energy and momentum transfer. So this is the result for the energy or momentum transfer. First plot is the recoil energy as a function of the dark matter and fixed mass difference. So as you can see, the minimum or maximum recoil energy is almost same as the mass difference. And then the difference between maximum and minimum recoil energy is smaller than, let's say, in this case, 0.05 K electron volt. So of course, if you increase mass difference, the difference between minimum and maximum recoil energy gets larger, but still the range of the recoil energy is limited. And for the momentum transfer, for instance, for when the mass difference equal to 2.5 K electron volt, then the momentum transfer is about 50 K electron volt, and it's very monochromatic, as you can see from here. The range, the recoil energy delta Q is the difference between minimum and maximum momentum transfer, which is very small. So we can compute the dark matter event rate following the standard technique. And here, total cross-section is the input for elastic scattering cross-section. But here there are two important factors. One is the atomic enhancement factor, including the fact that the electrons are bound, and the phase space factor. There is an enhancement factor in the for the electron and dark matter scattering. So, and here for atomic enhancement factor here, this plot shows the ionization form factor scale as a function of the recoil energy for electrons in the outer shells, 3, 4, 5. And here we are comparing our result in solid lines with the result Bloch et al. In dashed lines. So they are almost they are both consistent. In particular, there is no difference around the peak and beyond the peak energies. And here, as I said before, for when the mass difference is about 2.5 K electron volt, the momentum transfer is peaked around 50 or 60 K electron volt, and this form factor contribute from the peak in this case. So the event as the for the summary for the scattering cross section, or we can summarize here total event rate per detector in this expression here. It depends on the atomic enhancement factor and the dark matter energy density, and the scattering cross section normalized to the one for elastic scattering and the mass difference. Of course, in this case, the recoil energy is almost monochromatic, as I said before. But because of the detector resolution, we have to include the detector resolution and efficiency. So then we can draw the signal on top of the background shown in red, and the signal plus background shown in this bump, depending on the value of the cross section. So let me switch to the dark matter models, in particular effective field theory for exothermic dark matter. So this is very simple effective field theory for Schroeder-Dirac fermion. Here, there's a G prime exchanges between chi1 and chi2 with the general vector interactions, vectorial or pseudo vector interaction, and G prime also coupled to electron. Neutrino interaction is not necessary, but here neutrino interaction is included for generality. Then we can compute the dark matter electrons elastic scattering cross section in this form. Then you can see the ballpark value of the electron coupling and G prime mass, etc. So the G prime mass below sub GeV, and also light dark matter is favored by considering bound from current experiment. So in this case, there are two things to discussed, there are astrophysics bound on the lifetime of the heavier state, and the dark matter radiative density and other terrestrial bound are also important. So first thing is the astrophysics bound. So we need the heavier dark matter to exist, and then the heavier dark matter scatter with the electron to produce recoil energy in the first place. So here, if in the presence of the axial vector coupling for electron, we need to consider two-photon decay of the heavier particle going into the lighter particle. So, but there is a strong bound diffuse X-ray searches. So if this two-photon channel is open, there's a strong constraint. And then also there's a three-level process for heavier state to decay into two neutrinos. In this case, we only have lifetime bound, because super K and other neutrino experiment are not sensitive enough to the neutrinos with the energy about K electron volt. So, and then let me now go to the dark matter radiative density. So dark matter radiative density, just I introduced effective couplings for G prime between dark matter and J prime, and between electron and J prime. So it is necessary dark matter for dark matter to annihilate into the standard model particles, electrons, and neutrinos. And the dark matter pair also annihilate into G prime pair. So these two channels are necessary by construction. And but there is important bound because of the late chemical decoupling between heavier state and the lighter state. Because of the hidden, the dark matter coupling to G prime tends to be larger. So this channel would be decoupled at a very late time, even after it can decouple very late time. And then if once the dark matter decouples, the dark matter temperature scales differently, T square divided by kinetic decoupling temperature. So in this case, this G prime coupling divided by G prime mass is bounded in this way.
Hi, Hugh. So just to let you know that you have 5 minutes.
Okay. Okay. Thank you. So let me go to the dark matter self-scattering. So of course here, for the same channel, for I call this dark matter self-annihilation between dark matter component. The same channels are also relevant for the dark matter self-scattering. So if both of them exist now, then we cannot distinguish between them, and they just self-scattering, and then they kick themselves to avoid peaky, the Cosby profile of dark matter distribution. So there are elastic self-scattering and inelastic self-scattering and elastic self-scattering, and both of them will contribute to the dark matter self-scattering. And the important thing is that there is a G prime resonance, which make dark matter self-scattering to be velocity dependent, as you can see from here. And if you put everything together, including collider searches for visible or invisible G prime and beam dump and meson decay, etc., then you can see that the strong bound from bar invisible or visible searches, and then there's a bound on the late decoupling of dark matter annihilation here. So, but nonetheless, we can see some parameter space for which we can satisfy the relic density, correct relic density, and the G-non one-to excess. So here, as I said before, I just assume that there's mass splitting between the two component dark matter. but this can be naturally realized when you include Majorana masses for Dirac particles. So when the Majorana mass is much smaller than Dirac mass, then we can get a very small mass splitting between the two components as well. And then we also have flavor changing interaction in the dark sector because of G prime interaction. So G prime portal can be introduced to communicate between dark matter and the standard model by introducing gauge kinetic mixing here. Then we don't have actual vector coupling, so we are safe from diffuse X-ray bound. We only have a vector coupling to electron. So, and then the neutrino, the dark matter decaying into neutrino, the decay rate is sufficiently large, so sufficiently small, so the lifetime is very long. So I have another model for realizing for G prime portal in a different way by including vector like lepton. But let me go to the more interesting part, which will be published tomorrow. So dark mesons. So I'm switching to another model, a completely different model. Here, when there are light dark fermions in the dark sector, which dark quarks could condense to form dark mesons after dark QCD condensation. So, and then the resulting dark meson masses depending on the dark quark masses M1, M2, M3. So if somehow there's a dark flavor symmetry for equal dark quark masses, resulting dark meson masses are equal, and we cannot distinguish between dark mesons. So then there's the accidental flavor symmetry protecting dark meson from decay. But of course, the dark mesons could respect the full flavor symmetry. This flavor symmetry is somehow broken when we want to communicate between dark meson and the standard model. So G prime interaction could U1 prime can gauge the dark flavor symmetry partially, but we want the dark meson not to decay, so we don't want the chiral anomalies in the dark sector. So for the appropriate assignment of dark quark charge Q prime here, this is not identity, but this non-universal form of the dark quark charges can be assigned. In this way, we can make the dark matter to be kinetic equilibrium with the standard model particle. And of course, here on up to here, we assume that all the dark mesons to be mass degenerate. But the when you include the flavor mixing in the dark sector, after U1 is broken, we can generate the orthogonal component in the mass matrix for dark quark. Then we can induce mass splitting between dark mesons. Of course, since we are gauging the flavor symmetry partially, it's necessary to include G prime gauge corrections to the meson masses. So we want to control the mass splitting only by the flavor mixing. We want G prime correction to be subdominant. So then we have a constraint on the G prime mass. So if you go, since the point is that the mass matrix for dark quark does not commute with the dark quark operator. As a consequence, it is necessary to have a flavor violating coupling between dark mesons after diagonalizing the dark meson mass matrix. So because of that, we can realize exothermic dark matter electron scattering. Here, I forgot to mention that there are the pions, dark pions dark pion masses are split, and then the dark kaon masses also split. But these two masses are correlated but they are not equal. So because of that, there are two bumps in the dark matter electron. Sorry, there are two bumps in the dark matter electron recoil energy. So one peak, suppose if you fixed one peak at 2.3 K electron volt, then there appears another peak at 4 K electron volt. So we try to fit the genome one-ton data with two peaks as compared to one peak scenario. So in the case of one double peak scenario, it fit the genome one-ton data better with a lower chi-square value. So in this case, there are strong bound from late decoupling and G prime mass corrections. So as you can see here in this plot, the gauge connecting mixing versus G prime mass. So red line satisfies relic density, and the black line we can satisfy genome one-ton excess. And then here blue region is excluded because the G prime mass correction is too large. So we have some limited parameter space, which is okay with all the constraints. So of course we can open more parameter space by making the decoupling to be earlier. So we can solve the late decoupling by including new light fermions, or we may have some protection symmetry to stabilize we can stabilize G prime mass correction.
So Hyun, so just to let you know that will you have time also for discussions later on?
Okay,
But,
yeah.
Okay,
so,
you
okay,
reach the conclusions, fine.
Yeah, let me conclude now. Yeah, sorry. So we consider downscattering of exothermic dark matter to explain genome electron excess, and then to explain the genome one-ton excess with the exothermic dark matter, it is necessary to consider light dark matter and mediator. And I proposed pseudo-Dirac dark fermion to explain genome one-ton excess, and this dark fermion could be self-interacting with the velocity dependence. And the dark mesons could have approximate flavor symmetry such that the mass splittings could be stable under the radiative correction and producing more than one peaks in the electron recoil energy. Okay, thank you very much.
All right, thank you, Hyun. So we have time for one question. Anyone?
Yeah.
I have a question.
Okay.
Can you hear me? So thanks for the talk. So we're wondering, you have these two bumps because you have these two mass difference, right? In the meson.
Yeah.
But why only two? I mean, I guess you will have much more mesons, right?
Yeah, there are more mesons, but here because of the charge assignment, like a kaon, you have a charged kaon and charged pion for three quark flavors, as in the standard model. And then here, this is the before this epsilon prime are introduced. When there is no flavor mixing, we have these two charged G prime interactions, one for charged kaon, one for charged pion. And then after diagonalizing the meson mass matrix, then we can induce only flavor changing G prime interaction for pion or kaon sector. So therefore, because of that, these two states, one for pion-like dark mesons, one for kaon-like dark mesons. So these two are relevant for exothermic dark matter.
Okay, I see. Thanks.
But these two mass differences are correlated in this case.
All right, thank you so much, Hyun. So now we move to our next speaker, Xiaoyong. He will also talk about self-interacting dark matter. Could you please share your screen? Yes. Okay. All right. So take your time. Remember, when you have 5 minutes to be done, then I will remind you.
Okay. Thank you.
All right. Bye.
You can see my screen and everything, right?
Yes. Yes.
Okay.
That's good.
Okay. First, I'd like to thank Nicola for this kind invitation. Although I cannot be there this year in person, I hope I can visit soon. Yeah, my topic will be about the parameterization of dark matter self-interactions. This is based on the work I've done last year with Camilo, which is also the next speaker, and Hitoshi Murayama. So first, I will give a brief introduction. As Hyun Min Lee already gave the motivation for self-interacting dark matter, so I'll be simply brief. So at this point, we only observed the existence of dark matter from astrophysics and cosmology. So since we haven't seen any evidence or any convincing evidence from local experiments, so we may ask, what else can we actually learn from astrophysics? Indeed, there are actually several puzzles, as previously mentioned, especially like several puzzles at small scales, which you should refer to as small scale problems because they appear at astrophysical scales usually below cluster size. One of the example is this apparent mass deficit in small scale halos, especially in the center. It includes a co-Kasper problem or too big to fail. So as we all know pretty much now, and one explanation is to introduce self-interacting dark matter as to introduce the scattering among dark matter particles to increase the entropy to push dark matter away from the center. So to achieve such observable effect, you basically need dark matter self-interaction of the scale is centimeter squared per gram for elastic scattering cross-section over dark matter mass in these small size halos. And this number is not actually a surprise. This is basically what's the number you need to get one dark matter particle to scatter at least one times. So to have some observable effect. But on the other hand, there have been strong constraints from larger scale observations, especially for clusters. As the first panel shows, because when two cluster merges, their host halos would lose energy if their dark matter also scatters. And also it would also induce like mass deficit in very larger halos, cluster size halos, which are not observed at least at the moment. So that would lead to constraints on such self-interaction about 0.221 centimeter squared per gram for larger cluster halos, let's say. So if you compare these two observations together, it tends to suggest there is some velocity dependency in such dark matter interaction that is needed to contain both observations. So basically, when I said the parameterization of dark matter self-interaction, I mean the parameterization of this velocity dependency. And this velocity dependence has been achieved in various models. The two dominant ones is the one using a light mediator, which is not a surprise because if you have two dark matter particles scattered by a T-channel exchange of a light mediator, naturally, you would have both an enhanced annihilation scattering cross-section and also some velocity dependency, especially enhancement at small scales. In non-relativistic case, you could, in this light mediator case, you can in general characterize it with the Yukawa potential, which is given here. So it can be like either attractive or repulsive. So even in such very simple models, you can see the calculation can actually be quite complicated, as we all know now. And of course, the easiest region is just when the coupling is small, as given is usually referred to as Born region. So when the coupling is very small, you can just use a first order Born approximation to do that calculation. By increasing the coupling, at some point, you will get some non-perturbative effect, especially for attractive force. So this is the second region now, which is referred to the resonant region, but actually it's a abundant state formation. So in this case, you can still have very low velocity, but the coupling is larger, so some bonding state tend to form for attractive force as the intermediate state, which changes the behavior of self-interaction. And then you can just keep increasing the velocity, then you would reach this so-called classic region. What happens is actually the velocity is larger enough, so it reduces the W wavelength of dark matter. At some point, the W wavelength is smaller than this potential range, which is characterized by the inverse of mediated mass. So it means multiple scattering can happen during the dark matter scatter with the potential of another dark matter particles. So this is several different regions. Each of them which require would have different behaviors for self-interacting dark matter. And another way to achieve velocity dependency, as already mentioned by Hyun Min Lee earlier, it's using a resonance, S-wave, S-channel resonance. So in this case, this is very similar to how you could enhance dark matter annihilation. You have a live mediator or you have resonance. So here you basically have two dark matter analyzed scatter with intermediate particle as channel. So when the media mass is close to dark matter mass times 2, of course, you could have an enhancement effect, which can be generalized in this Breit-Wagner resonance formula here. As already been showed, in that case, you would also have velocity dependency. So this is the two dominant cases. But here I was talking about how it's possible to generalize these various kind of models, especially those ones with finite range potentials. So here we need to go back to the textbook of quantum scattering theory. So for such a scattering at a non-relativistic limit, the cross-section can be characterized directly by the phase shift in the wave function. As shown by the figure, you have a wave, if a planned wave scatter with the potential of another dark matter particle, that would lead to a scattered part. So that is, in that case, the cross-section can be totally characterized by the phase shift. But there is an early observation in nuclear physics, which has been observed just after World War II by Schwing and Bass and Jackson and someone else. So the idea is basically for finer range force, the boundary condition would require the phase shift, tangent phase shift divided by this basically for S wave is just the key, would converge to a constant as extremely non-relativistic region. So this is valid for like at least for simple finer range force potentials. So this observation would allow you could expand the phase shift in a very simple way with the velocity of dark matter, as is shown in the last equations here. So it's the A is the constant, the first order part, which is also the constant part, is referred to as scattering length. And the second order part is usually called as effective range. This is why the theory is called effective range theory in nuclear physics. So in general, because we are dealing with non-relativistic cases, because dark matter are generally non-relativistic in dark matter halos, so it would means in general we would have S wave dominant. So we only need to know these two parameters, scattering length and effective range for S wave. For S wave, simplify S wave scatterings. So this would allow us, based on several approximation and assumptions, would allows us to have S wave dominant cross section is in general characterized simply in this way by two parameters. This is the effective range and scattering length, so which is RE and A. So in this case, you can see actually it's indeed what we need. I mean, first, if you have really hard scattering, like say the A is small and I mean, basically the potential is extremely high, or so in that case, you would have a constant cross section, which is just 4 pi squared. This is what applies to contact interaction. And on the other hand, if you have like resonance on SNLs, very larger cross section when it goes to infinity, so then the total cross section is regularized by 4 pi over k squared. It's basically regularized by unitarity bound. And on the other hand, if you plot the velocity dependency here, you can see the x-axis is the velocity dependency which increases along the x-axis, y-axis is just a cross-section in a normalized unit. So you could see in general, you would have at small velocity, you have a larger cross-section, a scattering cross-section, and a very large velocity, you would have small scattering cross-section. This is exactly what we need for the observation of self-interacting dark matter. So this is basic things of this parameterization. So one would ask whether it actually applies to those well-known dark matter models. So this section is how we verify them. And so you can see this is a cross-section, which is parameterized by 2 parameters. So obviously you could see it is definitely correct for contact interaction where the interaction is just constant. So this applies to effective operators or quadratic interactions. Also this so-called simple case. So that would be valid. And of course, for Born region, you could just solve the cross-section directly and then just compare these two to see whether it works. So in that case, actually, you can see actually it works. So by replace the scattering length and effective range by 2 parameters of this dark matter model, you could get exactly the same result for Born region of Yucca interactions. And to go a little bit further, you could also have it to apply to a more general Yucca potentials, including those you should call it a resonant region, and it does not follow classic regions. So analytically, what we did is because Yucca potential cannot be, the wave function cannot be solved analytically, so we parameterize it with Hawthorne potential. So in that case, we can also work out both the scattering length and effective range for this to describe like this resonant region purely with these 2 parameters. Numerically, of course, numerically we can solve this Yucca potential exactly. So this is what we got. The colored part is a numerical result by solving exactly the Yucca potential to get the self-interaction. And I guess the green part is the result we got by parameterized with 2 effective ranges series parameters. So we did it for, so the x-axis is just the mediator mass, y-axis is again the cross-section normalized by dark matter mass. So we did it for several velocities. So you can see at small velocities. Oh, by the way, the curves with resonance is of course attractive force, and the curve without resonance is a repulsive force by changing the sign of couplings. So you can see at small velocities it works really well, like 10 kilometers per second velocity. Even with 100 kilometers for this we choose, it works well. But you can see by increasing velocity at larger velocity cases, this numerical result does not agree with anymore. I mean, at least for small mediator region with the parameterization we got. So it means it does not apply to classic region, at least precisely. So then we, of course, you can also do it for this Breit-Wagner resonances of self-interacting dark matter, as I introduced earlier. So in that case, the S-wave cross-section is actually have a 1-to-1 correspondence with the parameterization. So of course, in that case, it can be described to, this is also known in quantum scattering theory for this kind of resonance. So at least for those cases, you could have it work. And but as I mentioned, you can see it does not work for some cases. So here we'll talk about a little bit generalization. Especially, this is a classic region, which is usually the mediator is extremely small, as you can see, smaller than several values. Then it goes to like long range force or even higher orders of scattering higher orders partial wave need to be taken into account. So for both cases, either needed to a more complicated modification of this effective range theory, which also has been studied in the literature, or you need to take into account those parameters for high L partial wave scattering. So in general, it would lead to too many parameters to make it much less interesting. And there are also other cases where it does not work perfectly, as this case, as you introduce a more complicated potential. For example, with your car potential, you can also maybe add another harder well or wheel to gravitation, sorry, not a potential well, a potential wall. So in that case, instead of being described purely by two parameters, it's actually introduce another constant piece plus this known effective range two parameters. So basically, you need another R. And so in that case, the scattering amplitude needs three parameters. And we have checked it works in this case, in these three parameter cases it works. And this three parameter parameterization also could apply to anti-resonances, which is beyond my talk. And another thing, interesting part is, as we know, we don't only have elastic scattering, we can also have like dark matter annihilations. So in that case, we know the phase shift will be imaginary. But what nicely is we know what the dark matter scattering we need is extremely larger. So in general, this imaginary part of phase shift will be small. So this would allow us to treat the imaginary part of this phase shift, sorry, I missed I here, as a splitting part. So in that case, you can actually using the both real part and imaginary part, that would lead to also two complex effective range parameters. So in that case, you could actually get some connections. This is for dark matter annihilation, which is defined in scattering theory like this, as a function of scattering cross-section, sigma over k, and with some parameters. So in some sense, it provides a possible connection between self-interaction of annihilation. And you can see these papers for more detailed discussion and some philosophy along the same line. So this is the generalization part. So then we can just try to study dark matter with such parameterization. Of course, at first is observations. At this point, as we know, the observation is not precise enough. So in the left panel, what we draw is actually once we fix the scattering cross-section as 1 centimeter squared per gram at extreme velocity, this is what we need for drop size halos. And then we use the bound from cluster observations. So here we simply take 1 centimeter squared per gram at very large velocities as a cluster bound. So you can see now it only excludes a very small parameter region. But of course, with the improvement of this measurement, maybe now we can say probably we are reaching 0.5 centimeters squared per gram at cluster level. So in that case, it would disfavor like dark matter mass below several MeV for reasonably small ratio of these two parameters.
All right, sorry for interrupt, but you have 5 minutes to go.
Okay, yeah, close. Of course, you can do the same thing with, I mean, just another way to do it using different observations to fit. So at small velocities and at larger velocities, and the y-axis is just a cross-section. So here you can see, I mean, you can do fit their parameter regions, which could fit both as obviously. So before, after that, I mean, I think also the most interesting part is actually this two parameter characterization could be used for simulations. This is because when we do simulations, we tend to simulate a big host halo with several satellite halos inside. So it means different dark matter in this halo would have different characteristic velocity. So far we are just choosing some models, or we just take constant self-interaction. But this case would allow us to really simulate such a complicated system at least self-consistently for dark matter models, and to take into account all those possible effects to see whether there's anything new. And this is the last part is pretty futuristic, so I'm not really commenting much. So once, like maybe in tens of years, we measure this such velocity dependency and we decide these two parameters, what we would gain. So one case is for weak coupling. If we actually measure A smaller than 0, a large RE, so it will actually tend to suggest it's attractive force. This is quite easy to see by study actually the scattering theory. So with the attractive force, you would have a larger momentum within the center, so which means a fast oscillation. So in that case, it will tend to suggest attractive potential. So which is shown in this figure. X-axis is vector range, y-axis is scattering range. So it basically says where those values should be at for different models. And for strong couplings, where actually you can have pole-dominant cases. So in that case, the cross-section would be dominated by poles for bottom state formation or resonances. So depending on the pole of these denominators, you would actually get some properties of this intermediate poles. So especially if you look at the time changing, if you have a solution like this, you would have a wave function proportional to this. So it means you have a physical intermediate states, but which decays away with time. So this is a resonance. And then in the other kind, you would have a negative energy, which is a abundant state, which decays away as larger R's. So, and the last part is unphysical solution, but it also affects the final effect. So I will not go there. And now I come to my conclusion. So basically, what I said is there may be hints for non-conventional dark matter, at least self-interactions at small scales. So it seems at this stage, the velocity dependency is an important part of model building of such cases. There have been several models, but in this case, we would suggest constant parameterization of them. So as you can see, although it does not describe all of those models, but it's able to cover most of them, at least for those well-motivated ones. And this will allow us to run the simulation more precisely, maybe to see some new effect. Of course, future observation and precise simulation would be crucial to decide whether we really have self-interactions or not. Thanks. So I'm done.
All right, thank you very much. Right on time. So we do have times for questions. Please just unmute your microphone and ask.
Hey, Young, I'd have a quick question. So this hard wall scattering, when would it be important? Is it? I mean, I'm thinking sort of on nucleon type potential. So would it be important for dark matter being some form of a dark QCD bound state where you have light mediators and in addition sort of a hard nuclear force, or what would be the application?
Yes, yes, this is basically this is contact interactions. So yes, for like hydrons, so in that case, if the cross section, as I mentioned earlier, I would describe this SIMP, I guess this SIMP, I don't remember what it means. It's two cases which usually are dark nuclear interactions.
Thanks.
All right. Further questions?
I have one.
Okay.
Could you please, Young, go to your last slide where you show the plot of the scattering length versus the effective range?
Sorry, this one or which one?
One, I think. Exactly, virtual levels. What's that?
Actually, it's something. I mean, it's a solution of this denominator to be 0, but it does not correspond to a physical state because you can see in this case, I mean, when the solution have this minus k, so the potential, the wave function actually goes exponentially increasing, which is non-physical. But you could see such a pole in the, in the scattering cross section. So this is in condensed matter is usually referred to virtual states or virtual levels. Yeah, so it's not a physical state, but it has some effect as intermediate effects.
But can I follow up? Is it like a zero energy bound state, or?
Yeah, it meets the bounding state at E equals 0. So, I mean, when energy goes to 0, which basically means when K goes to 0, so it would meet the bounding state there. So you can see for bounding state, you have a positive IK, and for this one, you have a negative one.
Okay, thanks.
So I have a quick, can I ask a quick question?
Yeah, sure.
What happens to this parametrization when you have a P-wave dominance?
Oh, I mean, if you have this, okay, we just go to rest. So as you can see here, like for each L partial wave, you would have 2 parameters. I mean, in this case, we consider S wave dominant. If assuming it's always P wave dominant, you could just take A1 and RE1. So in that case, everything is parameterized by these 2 parameters for P wave. You can just put them in the scattering amplitude. But of course, okay, if you assuming there are many partial waves contributes, it will lead to so many parameters, which would make this parameterization less interesting.
Okay, thank you.
All right, so thank you so much. Let's move to our next speaker, Camilo. Camilo, it's good to see you again. Long time no see, even if it's remotely.
Yeah, I'm sorry that I can't be in Brazil. I was there, I think 4 years ago, and I had a great time. Unfortunately, this time has to be virtual.
Yeah. All right. So take your time. Remember, I'll give you a 5 minutes warning.
Okay. So can I start now?
Yeah, sure.
Okay. I'm very sorry for this. I don't know. There was a very strange noise. So, okay. My name is Camilo Garcia-Cely. I'm an Alexander von Humboldt Fellow in DESY Hamburg. And I'm going to tell you about inelastic dark matter and a dark Higgs. So this is work based on some paper that is going to be in the archive very soon, hopefully before the end of the year. And it was done in collaboration with my colleagues in DESY, in particular, Michael Dürr, Torben Ferber, who is a Bell 2 experimentalist, Christian Harty, and Kai Schmidt-Hoberg. Okay, so before discussing inelastic dark matter, let me motivate a bit my talk by considering the thermal dark matter paradigm. I'm sure a lot of you are familiar with it, but I will just anyways review it. So here the idea is very simple and very predictive. So if we assume that the dark matter has a strong, sufficiently strong couplings to the standard model, in the early universe, it might have been in thermal equilibrium. And then at some point, as the universe evolves, the dark matter decouples. And you see that the thermal density associated to that is constant. So in this plot is denoted by Y on the left axis or by omega X on the right axis. And it's very predictive because this is one of the only things we know about dark matter is relic density today, about 0.1. And this immediately tells us the scale of dark matter, if this paradigm is true. So it tells us that the annihilation cross-section must be of the order of 3 × 10⁻26 centimeter cube per second. It tells us that the cross-sections must be of order picobar, and it tells us the mass. So it goes from sub GeV to 200 TeV masses. So this is very interesting, and of course is extremely motivated. This has driven the community for decades by now. But of course, this paradigm is under severe tension. And the reason is, well, precisely because we know where to look. We have very stringent constraints. And in particular, direct searches of these thermal candidates, or rather particles interacting with cross sections around picobar, are extremely, so these constraints are extremely strong. So on the upper plane, I show the dark matter, for instance, the dark matter electron cross section. And if we assume that this cross section is of the order of picobar, you see we have very strong limits. So we typically have, if we want to evade those bounds, we typically have to go to small masses. Typically masses of the order of, so the sub-GeV scale. By the way, I took this plot from some of the people who will speak about this later in the conference. So this is a nice way to motivate sub-GeV dark matter. Now, what is the problem with this? The problem is that if we go to low scales, so if we go to this to the sub-GeV regime, we immediately find problems with indirect detection. In particular, dark matter could annihilate and into electrons or photons, and if such annihilation is the same during CMB times as it was during the time when dark matter was produced, we are immediately excluded. Such a thing is immediately excluded. Okay, so we have to avoid constant cross sections, or as they are typically called, S-wave cross sections. So we need to have some sort. If we want to be at this, if we want to have thermal dark matter at the sub-GeV scale, we need to ensure somehow that there are no annihilations during the CMB times. Okay, and that's what inelastic dark matter does for you. So that's actually the motivation for considering inelastic dark matter. The idea is relatively simple. Essentially, what we do is we consider dark matter to be some sort of fermion, a Majorana fermion. We call it Chi1. And then this dark matter particle has an excited state, a heavier twin, Chi2. Okay, so the interactions are of the standard model with the dark matter are inelastic. So anytime that Chi1 interacts with the standard model particles, it's converted into Chi2. So due to this, we can evade direct detection limits. And in particular, we can also evade CMB constraints. So this is a very nice scenario of thermal dark matter that is not excluded by direct detection or by CMB observations. Okay, so how do we construct a model for that? Well, let's start with a Dirac fermion charged under a U1 symmetry. And then this Dirac fermion, it's split into two components, Chi1 and Chi2. So the Chi1 component is the dark matter, as I already said, and the Chi2 is an excited state. Now, because of this U1 symmetry is broken, we get a dark photon, so a particle that has a massive gauge boson. And Chi1 and Chi2 interact in such a way with the standard model that, interact via this vertex that I show here. So this happens in such a way that anytime that Chi1 interacts, it produces Chi2. So if there is a mass splitting, this allows to evade direct detection constraints. Okay. Now, this is just one of the many possibilities to connect sub-GeV dark matter to the standard model, right? In fact, we know there are three models, and we can classify them according to how they connect to, according to the operator to which they connect to the standard model. For instance, a dark photon connects via the so-called kinetic mixing, and is really a coupling between a gauge field strength tensor and the B field of the standard model, which is a singlet. We have more singlets in the standard model. Another singlet is H dagger H, and that's the so-called Higgs portal. And another singlet, it's the neutrino right-handed. So the doublet right-handed doublet portal, right? So LHN. Okay, so in the specific example that I was discussing before, I was talking about the hypercharge mixing with this field strength tensor from the dark photon. Okay. Okay, so typically what you do is you write down this coupling and you work out the masses of the dark photon. And if you do that, you obtain a theory in which this A prime couples to the standard model fermions via the electric charge and some common factor epsilon. Okay. So how does the phenomenology of this looks? So if we consider thermal dark matter, in this scenario, you can easily produce the Rayleigh density via this static excited state. So in the early universe, we have Chi1 and Chi2. They annihilate via an X-channel dark photon into standard model fermions. That's a thermal process. And if we assume that the dark photons are heavier than the dark matter, then the dark matter does not annihilate into the dark photons. Actually, a propagator is in my screen. A propagator is missing, but it should be two dark matter fields going to two dark photons. So we forbid this process by taking the dark photons heavier than the dark matter. Okay. Now, okay, why do we want to consider this? Because, okay, so this is not proved by direct detection. It's not proved by indirect detection experiments, in particular by the CMB constraints, but they can be searched for in colliders. So there are collider signatures of this scenario that are very interesting. These are typically displaced vertices, and this was investigated by my group last year, actually. And the idea, so on the left, you have the Feynman diagram associated to the process that you look for in a collider. This is how theories look for something. They draw Feynman diagrams. On the right-hand side, you see what actually happens in real life. So these are just two representations of the same thing. On the left, you see we have a collision of E plus E minus. Then some photon is radiated away from the positron. But then we have these S-channel processes induced by the dark photon. And the dark photon decays into Chi1 and Chi2. The Chi2 decays further into Chi1 and an off-shell dark photon. And this dark photon decays in a detector inside the collider experiment, producing E plus E minus pairs or mu plus mu minus pairs. And yeah, so on the right-hand side, I just have exactly the same thing, but it's more like a real representation of what happens. Okay, so, but that's not what we do in our current work. What we did in our current work was to address a few open questions in this scenario of inelastic dark matter. And of course, these are very obvious questions, but somehow this was not, they were not addressed in the context of searching for these signatures in colliders. So one obvious question is, okay, you have a dark photon. How does it get its mass? The other thing is, for this inelastic dark matter scenario to work, you need a mass splitting between Chi1 and Chi2. How do you get such a mass splitting? And how does it affect the phenomenology? The simplest possibility you can imagine is to consider the dark Higgs mechanism. So the dark Higgs mechanism just allows you to give a mass to the dark photon in exactly the same way as the Higgs mechanism gives masses to the standard model gauge bosons in the visible sector. And typically what you do here is, okay, you write down your Mexican hump potential. Now we need this in 2 dimensions. One piece for the Higgs doublet, another piece for the scalar doublet breaking the dark symmetry. And okay, obviously when you do that, then automatically you open the second portal, the scalar portal. And this is very interesting because that means that we can constrain this inelastic dark matter using two portals. So you have actually now two parameters that control the phenomenology. One is the parameter associated with the kinetic mixing of the gauge bosons, and the other one is the scalar mixing angle between the dark Higgs and the dark Higgs. Okay, so yes, okay, let me go back here. So if you write down the Lagrangian, you find that by doing this, you not only have inelastic interactions, but also elastic interactions. So you have to be careful because then by introducing these elastic interactions, you might spoil the nice features of inelastic dark matter. Let's see, let's go one by one. So one of them is, for instance, annihilations, right? So if you introduce this couplings between chi1 and chi1, then you have annihilation into scalars, and that could be problematic if they are constant during the entire history of the universe. But as I just said, that's not really a problem because these processes are p-wave suppressed. So even if they were significant during the time when dark matter was produced thermally, they the corresponding cross-section decreases with time, and in particular is very small during the time of CMB formation. Now we also have elastic scattering, and we could have the scattering of dark matter of quarks of the standard model induced by this dark Higgs, but this is momentum suppressed. So, okay, even though we introduce this dark Higgs and we introduce elastic interactions, this does not spoil the nice features of inelastic dark matter. And what is more interesting is that this opens up a lot of parameter space. So in the case where you only have the dark photon, you need to have always small mass splittings to produce the relic density, and you don't have as many, you cannot probe as many dark matter masses. Now, when we do this, of course, we introduce more parameters, which means we open up parameter space for the dark matter. In particular, we allow for mass splittings that are much larger and for a larger mass range. Okay, so as I told you before, our motivation was to look into the consequences of the dark Higgs mechanism in a collider. And so my colleagues here in Hamburg, they are interested in BEL2. I mean, two of them are experimentalists from BEL2, which is a collider. It's a big factory in Japan, very close to Tokyo. And what is good about this is that we will have a high luminosity in these experiments. And these are E+, E- colliders. So one can really probe precisely dark sectors with these sort of machines. And I will show you that in a minute. So one particular example that was of interest to us was this displaced vertices. And okay, so we in our study, we included this displaced vertices, but this displaced vertex actually is only one, does not involve the dark Higgs. This H-, H+, they're correct. These are just, this stands for hadrons. So here, nothing involves any dark Higgs. So we consider this signature, but in addition, we consider a signature associated with the dark Higgs. And this is where things become very interesting. So essentially what we produce or what we study is the production of the following process. So we have E+, E-, then we have a Higgs stratum. So a dark Higgs is emitted from the dark photon, and then the dark photon produces a displaced signature. And actually, in this case, we have two displacements. So one associated to the A' itself, like it happened in the previous example. So arising from this upper leg, where chi2 decays into chi1 and then a dark photon. This produces a displaced vertex that we can search for. But one can also produce a displaced vertex from the decay of the H prime itself. Now, this is very interesting because anytime you produce this sort of, anytime you have these sort of processes, the background is from the standard model is very low. So essentially, observing one of these things would be like a smoking gun signature for dark matter in a collider. Okay. So now we put this in the typical planes in which portal dark matters are studied. So one of them is the dark photon plane, in which you have the kinetic mixing on the vertical axis and the dark matter mass on the horizontal axis. So actually, in this plane, the best limit so far is the one associated with Babar monophotons. And you see, this is there is a substantial difference between this limit and what you can do with Bell 2. In this scenario, so here I include three lines. One is the typical monophoton search, but you also have this displaced monophoton, which was the one I introduced at the beginning, that does not require the dark Higgs mechanism. And then in red, I show the monophoton signature that includes the dark Higgs. And then this is shown for two luminosities, 100 inverse femtobar and 50 inverse attobar. So this is these luminosities correspond to what could be observed next year. That's 100 inverse femtobar, or at the end of the decade, so 2030. So what I'm trying to say here is that if this is dark matter, if dark matter is inelastic and interacts via the dark Higgs mechanism, then one should be able to probe the kinetics mixings that are shown on the screen. Okay, I found this very interesting. But you can also do the same thing in the dark Higgs plane, right? Because now we have two portals. So here in this case, I'm showing the mixing angle versus the dark Higgs mass. And again, I show the results for 100 inverse femtobar and 50 inverse attobar. That corresponds to the thick dash line and solid dash lines. And in this case, you cannot get this for this parameter range.
Camilo, just 5 minutes to go, okay?
Yeah. So for this parameter range, there is no monophoton and no displaced monophotons. So you can only get this via the displaced signature induced by the dark Higgs. And what is interesting is, for instance, in this cyan color, what it's labeled as BKH prime, we show what could be done for the same luminosities if we have a dark Higgs with a given mass and a given mixing angle. And as you can see, having inelastic dark matter allows to probe a much broader parameter space. And in fact, one can even reach very small values of the mixing angle. Even so, I mean, if we that's the plan actually. If you look at the plane on the right, by summer 2021, we should be able to probe the mixing angles of the order of 10 to the minus 6, which of course is very interesting. Okay, one can also study other planes. For instance, here we have how this signature looks in the dark photon, so the dark photon mass, dark Higgs mass plane. And you see one can probe the thermal relic. I mean, actually, in all of these planes, there are thermal relic lines. So this is the parameter for which you can produce the dark matter thermally. And same thing in this plane. So again, this looks pretty promising. And even next year, one should be able to probe this with the data that will be collected by them. This is another plane. This is the plane in which we have the relic density. Actually, you see the relic density line. And yeah, the whole plane will be probed with 100 inverse 10 to 1 in the coming months, depending on when the analysis is done by the experimentalist. And notice that this corresponds to very small angles. So angles of mixing angles between the dark Higgs and the visible Higgs of the order of 10 to the minus 5. Okay, so these are my conclusions. And yeah, I just wanted to say that inelastic dark matter is a well-motivated thermal dark matter candidate at the sub-GeV scale that is that can evade the stringent limits from CMB and from the detection, but that nevertheless has very interesting signatures in colliders. And in particular, I investigate the implications of including a dark Higgs. And I study this, we study this displaced vertex signatures at Bell 2. And all this looks very promising. And we are putting everything together, and the paper should be in the archive very soon. And with this, I finished, and then I can take questions.
All right, thank you very much, Camilo. We have time for questions. Anyone?
Yeah, actually, sorry, can I ask one?
Sure.
Yeah, of course.
I just want, I mean, in this case, in principle, you could have like two scalars, right? Because one give you the original mass and one give you mass splitting.
No, the same scalar that gives the, in this scenario, the same scalar giving the mass splitting gives the mass to the gauge bosons. So, and actually that's the reason why you can have this displaced vertex signature, right? Because this displaced vertex signature depends on the mass splitting, and the mass splitting depends as well on the parameters that determine the dark photon mass. So that's why you can study all this. I mean, all this is tied together.
You're just playing with the Yukawas, right? To get
there is only one Yukawa. There's F that you see on the screen.
You already have, okay, so you already have the original Dirac mass.
Yeah, exactly. So you, exactly, I didn't write, or did I write it?
Oh, okay.
Wait, I think I wrote it. No, I did not. So, sorry. So I wrote the Lagrangian after symmetry breaking, but before symmetry breaking, you have a Yukawa coupling, which is this F from here, and you have a Dirac mass term. And what the Yukawa coupling does after symmetry breaking is to split the masses of the dark fermions in such a way that you get this inelastic interaction.
Thank you.
Okay.
Okay, further questions?
What is the, can I ask a question?
Sure.
So what is the typical mass splitting that of your interest?
Yes, okay, so the thing is that, okay, so when you don't put the dark Higgs, the mass splitting is determined from the Rayleigh density by the process that is the Feynman diagram that is there, so the one that says thermal process. And for this case, if you really want to produce the Rayleigh density to its current value, the mass splitting must be very small. Of course, this is a co-annihilation process, so the mass splitting must be sufficiently small for this process to be relevant in the early universe. Now, once you put the dark Higgs, then you open a new P wave channel. So you have chi1 going to H prime, okay? So that means that now the mass splitting does not need to be small. This is very good news for colliders, because that means that the collider signature will be much stronger. So in all these planes, I show the mass splitting. For instance, in the ones that I'm showing right now, the mass splitting, we just chose the mass splitting to be equal to the dark matter mass. So it's a very large mass splitting, but this is okay because it allows the thermal relic density. And in this particular case, it's 2.5. Now, in this plot, the one on the right, we vary the mass splitting. So the mass splitting is, in this case, in between 10 to the minus 1 and 2 for what we could be observed next year, relative to the dark matter mass.
Okay, thank you.
Yeah.
I have a question, Camilo.
Yeah.
Yeah. I like a lot the talk, but I have a question very naive. In the case that your dark photon, because in your model you consider that it couples evenly for all the leptons. So what happened in the your constraint also apply in the case that you have a dark photon that also only couples to muons and taus, for instance, that there are other type of models in this case?
Yeah. So yeah, I actually don't know, but because we were focusing on these portal scenarios, right? And in these portal scenarios, you couple the standard model fields in singlets. So for instance, the hypercharge is a singlet, right? It's a gauge singlet. So then you don't have information about families or things like that. Oh no, you can, of course, you can invoke a particular model and, for instance, couple this to B minus L or to L mu minus L tau. That's possible, certainly. But I don't know what the phenomenology in Bell2 would be if you have such things. Yeah, that's...
Yeah, because I was when you showed the diagram with the displayed vertex. So in some sense, if it couples only to muons and tau, could be kind of...
Okay. So it's not. Yeah. Okay. Well, but this is just a question of mass. So of course you can also produce electrons. So the dark Higgs can decay into electrons. But the problem is that that you will not be able to detect this just because the decay rate associated to that is extremely long. I mean, the Yukawa of the electron is very small, therefore the decay rate is very small, and the decay, the associated decay length is extremely large. So you don't see that process. I mean, in a collider.
Okay, I see. Thank you.
Yeah, you're welcome.
Okay, all right. So thank you so much, Camilo. Now it's time for a break.